Hello learners. Previously, we studied about the chemical reactivity of group 14 elements towards oxygen and halogens mainly. We also learned about the anomalous behavior of carbon along with some important allotropes of carbon, namely diamond, graphite and fullerenes. In this last session, we will study about some of the uses of carbon in the form of graphite, coke, charcoal, diamond and carbon black. We will also learn about the carbon monoxide and carbon dioxide, their basic properties, structure and uses. We will continue our session with compounds of silicon such as silicon dioxide, silicons, silicates and zeolites. As we learned about the carbon, its allotropes and their properties, we must also know about their uses. So, let us understand the uses of carbon. Graphite fibers embedded in plastic material form high strength, lightweight composites. The composites are used in products such as tennis rackets, fishing rods, aircrafts and canoes. Being a good conductor, graphite is used for electrodes in batteries and industrial electrolysis. Crucibles made from graphite are inert to dilute acids and alkalis. Carbon black is used as black pigment in black ink and as filler in automobile tires. Coke is used as a fuel and largely as a reducing agent in metallurgy. Diamond is a precious stone and used in jewelry. It is measured in carats. Being highly porous, activated charcoal is used in absorbing poisonous gases. Also used in water filters to remove organic contaminators and in air conditioning system to control odor. Next topic we have is some important compounds of carbon and silicon. The two important oxides of carbon are carbon monoxide, which is CO, and carbon dioxide, which is CO2. And for compounds of silicon, we have silicon dioxide, silicons, silicates and zeolites. Let us start with carbon monoxide. Carbon monoxide is a colorless, odorless and almost water insoluble gas. It is a powerful reducing agent and reduces almost all metal oxides other than those of the alkali and alkaline earth metals, aluminium and a few transition metals. This property of CO is used in the extraction of many metals from their oxides ores. For example, Fe2O3 in solid state plus 3CO giving 2Fe in solid state plus 3CO2 in gas phase. ZNO in solid phase plus CO in gas giving Zn in solid form plus CO2 as gas. When we talk about the structure of CO molecule, as you can see on your screen, there are 1 sigma and 2 pi bonds between carbon and oxygen, that is carbon triple bond oxygen. Because of the presence of a lone pair on carbon, CO molecule acts as a donor and reacts with certain metals when heated to form metal carbonyls. The highly poisonous nature of CO arises because of its ability to form a complex with hemoglobin, which is about 300 times more stable than the oxygen hemoglobin complex. This prevents hemoglobin in the red blood corpuscles from carrying oxygen around the body and ultimately resulting in death. Carbon monoxide can be prepared by direct oxidation of carbon in limited oxygen on air. The reaction involved is 2C plus O2 giving 2CO. On small scale, pure CO is prepared by dehydration of formic acid with concentrated sulfuric acid at 373 Kelvin. The reaction can be expressed as HCOOH giving H2O plus CO at 373 Kelvin and concentrated H2SO4. On commercial scale, it is prepared by passage of steam over hot coke. The mixture of CO and H2 thus produced is known as water gas or synthesis gas. Reaction is carbon plus H2O at 473 to 1273 Kelvin giving CO plus H2. When air is used instead of steam, a mixture of CO and N2 is produced, which is called producer gas. Reaction is 2C plus O2 plus 4N2 at 1273 Kelvin giving 2CO plus 4N2. Water gas and producer gas are very important industrial fuels. Carbon monoxide in water gas or producer gas can undergo further combustion, forming carbon dioxide with the liberation of heat. Next oxide of carbon is carbon dioxide. Carbon dioxide is a colorless and odorless gas. In the structure of CO2 molecule, carbon atom undergoes sp hybridization. Two sp hybridized orbitals of carbon atom overlap with two p orbitals of oxygen atom to make two sigma bonds, while other two electrons of carbon atom are involved in p-pi bonding with oxygen atom. This results in its linear shape with both CO bonds of equal length 115 picometer with no dipole moment. The resonance structures are shown on your screen. It is prepared by complete combustion of carbon containing fuels in excess of air. Carbon plus O2 with supply of heat giving CO2, CH4 plus 2O2 at heat giving CO2 plus 2H2O. In the laboratory, it is conveniently prepared by this action of dilute HCl on calcium carbonate. The reaction is CaCO3 plus 2HCl giving CaCl2 plus CO2 plus H2O. On commercial scale, it is obtained by heating limestone. Low solubility of carbon dioxide in water makes it of immense biochemical and geochemical importance. With water, it forms carbonic acid, that is H2CO3, which is a weak dibasic acid and dissociates in two steps as shown on the screen. H2CO3/HCO3- buffer system helps to maintain pH of blood between 7.26 to 7.42. Being acidic in nature, it combines with alkalis to form metal carbonates. Carbon dioxide, which is normally present to the extent of approximately 0.03% by volume in the atmosphere, is removed from it by the process known as photosynthesis. It is the process by which green plants convert atmospheric CO2 into carbohydrates such as glucose. The overall chemical change can be expressed as 6CO2 plus 12H2O in the presence of light and chlorophyll, giving C6H12O6 plus 6O2 plus 6H2O. By this process, plants make food for themselves as well as for animals and human beings. Unlike CO, it is not poisonous, but the increase in combustion of fossil fuels and decomposition of limestone for cement manufacture in recent years seem to increase the CO2 content of the atmosphere. This may lead to increase in greenhouse effect and thus raise the temperature of the atmosphere, which might have serious consequences. For the uses, carbon dioxide can be obtained as a solid in the form of dry ice by allowing the liquefied CO2 to expand rapidly. Dry ice is used as a refrigerant for ice cream and frozen food. Gaseous CO2 is extensively used to carbonate soft drinks. Being heavy and non-supporter of combustion, it is used as fire extinguisher. A substantial amount of CO2 is used to manufacture urea. This is all for the compounds of carbon. Now, we will proceed towards compounds of silicon, which are silicon dioxide, silicons, silicates and zeolites. Let us start with silicon dioxide. 95% of the Earth's crust is made up of silica and silicates. Silicon dioxide, commonly known as silica, occurs in several crystallographic forms. Quartz, cristobalite and tridymite are some of the crystalline forms of silica, and they are interconvertible at suitable temperature. Silicon dioxide is a covalent three-dimensional network solid in which each silicon atom is covalently bonded in a tetrahedral manner to 4 oxygen atoms. Each oxygen atom in turn covalently bonded to another silicon atoms as shown on the screen. Each corner is shared with another tetrahedron. The entire crystal may be considered as a giant molecule in which 8-membered rings are formed with alternate silicon and oxygen atoms. Silica in its normal form is almost non-reactive because of very high SiO bond enthalpy. It resists the attack by halogens, dihydrogen and most of the acids and metals even at elevated temperatures. However, it is attacked by HF and NaOH. SiO2 plus 2NaOH giving Na2SiO3 plus H2O. Another is SiO2 plus 4HF giving SiF4 plus 2H2O. When it comes to the application of silicon dioxide, you must know that quartz is extensively used as a piezoelectric material. It has made possible to develop extremely accurate clocks, modern radio and television broadcasting and mobile radio communications. Silica gel is also used as a drying agent and as a support for chromatographic materials and catalyst. Kieselguhr, an amorphous form of silica, is used in filtration plants. Next silicon compound to learn about is silicones. They are a group of organosilicon polymers which have R2SiO as a repeating unit. The starting materials for the manufacture of silicones are alkyl or aryl substituted silicon chlorides, RnSiCl 4-N, where R is alkyl or aryl group. When methyl chloride reacts with silicon in the presence of copper as a catalyst at a temperature 573 Kelvin, various types of methyl substituted chlorosilane of formula MESiCl3, Me2SiCl2, Me3SiCl with small amount of Me4Si are formed, where Me represents methyl group. Hydrolysis of dimethyl dichlorosilane, that is CH3 SiCl2, followed by the condensation polymerization, yields straight chain polymers. The reactions involved along with the structure is expressed on the screen. Silicons, as you can see in the structure, being surrounded by non-polar alkyl groups, are water repelling in nature. They have in general high thermal stability, high dielectric strength and resistance to oxidations and chemicals. These silicones have wide applications. They are used as sealant, greases, electrical insulators and for waterproofing of fabrics. Being biocompatible, they are also used in surgical and cosmetic plants. Next silicon compound is silicates. A large number of silicates minerals exist in nature. Some of the examples are feldspar, zeolites, mica and asbestos. The basic structural unit of silicates is SiO4 4-, in which silicon atom is bonded to 4 oxygen atoms in tetrahedron fashion. In silicates, either the discrete unit is present or a number of such units are joined together via corners by sharing 1, 2, 3 or 4 oxygen atoms per silicate units. When silicate units are linked together, they form chain, ring, sheet or 3-dimensional structures. Negative charge on silicate structure is neutralized by positively charged metal ions. If all the 4 corners are shared with other tetrahedral units, 3-dimensional network is formed. 2 important man-made silicates are glass and cement. Next, one of the very important compound we will learn about is zeolites. If aluminium atom replaces few silicon atoms in 3-dimensional network of silicon dioxide, overall structure known as aluminosilicate acquires a negative charge. Cations such as Na+, K+, or Ca2+ balance the negative charge. Examples are feldspar and zeolites. Zeolites are widely used as a catalyst in petrochemical industries for cracking of hydrocarbons and isomerization. Example, ZSM-5, which is a type of zeolite used to convert alcohols directly into gasoline. Hydrated zeolites are used as ion exchanges in softening of hard water. Now, let's conclude our session by recalling the discussed concepts and facts. Graphite fibers are used to form composites which have application in tennis rackets, fishing rods, aircrafts and canoes. Graphite, being a good conductor, is also used as electrodes. Activated charcoal is used in adsorption of poisonous gases, organic contaminators, etc. Coke is used as a fuel and as a reducing agent in metallurgy. Diamond is a precious stone and used in jewelry. Properties, preparation, detailed structure and uses were studied for carbon monoxide and carbon dioxide as well. Preparation, uses and detailed structure were also studied for silicon compounds like silicon dioxide, silicates, silicons and zeolites. As we end our session, try to solve the following question. If the starting material for the manufacture of silicons is RSiCl3, write the structure of the product formed. The next question is, give one method for industrial preparation and one for laboratory preparation of CO and CO2 each. So learners, that is all for the P block elements in class 11th. Thank you. Happy learning.